different integers. Meaning 5 and 5 counts as 1, but it won't count as 2 because distinct. That's a good way of putting it. My definition isn't going to work on this one. 2 distinct integers. I take it like the arrangement is distinctly different, like clearly different. Which means you can, like there's a distinct difference between 6 and 3 and 3 and 6, but there's no distinct difference. Like there's no distinguishable difference between 5 and 5 and 5 and 5. Does that make sense, kind of? That's not very technical of a definition, but that's kind of an explanation for why it is what it is. I'll keep scrolling down. So we have 6 ways, 3 ways, 4 ways, 6 ways. I'll give you a second on. There's quite a few answers for 20, 24, 36, 46, and 54. Guys, this homework was number 57, right? Good. Absent today. Everyone here. Number 46, you guys can even tell just by looking at it, it was a repeat one, right? Was that the Mississippi one? Yeah. Keyword in number 58 is groups. The order didn't matter. Keyword in number 58 was groups. And 68 was the facial recognition thing, right? Is that right, the facial recognition? As far as how many different options for, I forget what it was like hairlines and noses and eyes, eyebrows, something like that? Oh, chins and cheek structures, that's right. And so a fundamental counting principle, all you had to do is multiply them all together. But then letter B said, what if was it the victim or the person trying to identify the perpetrator? What if they could identify, but they weren't sure about these 3 characteristics? Well, if they could identify like a 1 in each of those blanks, they could identify. They chose it, but they weren't able to choose these. There's still that many different faces in the facial recognition, so not so sure it's so helpful. Even if you're able to pick out one characteristic, just think of this example just kind of says, think of how many different options there are still out there. Doesn't mean you wouldn't recognize the person if you saw them, but anyway. So word to the wise, just in general, to always be aware. It's just a safe thing, to always be aware of what's going on, of the people around you. Maybe don't always have your head in your phone whenever you're walking around or in a public place. Might not be the safest thing possible, especially when you're at college and you're with all sorts of strangers. Carl. 54? 120. Was 68 our final even? Okay. Hold up your homework facing me really quickly. Let me see it. Hold it up. If you have section 9.6. Facing me. We got one. We got another one. No? Is this a different one? Oh, so that's a different one. Ryan, I got you.
Oh, you got me.
Wrong, Ryan. Becca, I got you. I mean, I got you too, Ryan, but it's not a happy grade. In the first page. I got you. Thanks, Rebecca. I got you. That doesn't count. I got you. I'm pretty sure you did that like while we were grading.
No, I did this earlier.
No. I'm sorry. I was talking to Colby as I was grading yours. I was multitasking.
No, I only did half.
Okay, I'll give you a half though.
Can I have the half?
One for all for one. So I should give you their 2 zeros? Oh, okay, so let's not do it that way. All right. My ones that did the homework, do we have any questions on the evens or odds that need further clarification or further explanation? David?
Just 24. I remember we were going over this.
Yeah.
Like the B, it says the first one can't be have like a 0 in it, and then it can't like have 2 repetitions. But like, why can't we have a 0 in the next one?
Because it's specific. I think it specifically just said the leading digit can't be 0. So that just means the first digit can't be 0. So think of it this way. The number of options for the first digit are 1 through 9. So 9 options. But then one of those numbers got used. So 0 through 9 is legal, but whatever number was already used is now illegal. So that's why there's 9. Then 0 through 9, but 2 numbers missing. 0 through 9, 3 numbers missing. So it's that keyword leading. Just the first digit had that restriction. The rest, because I can have 1,000 and there's no 0 at the beginning, even though there's 0 somewhere else. Melanie. Good question. Can you give me what kind of problem it was? What was going on?
So it said you randomly select 5 students from a class of 20 and how many different groups of 5 students are possible.
Okay, so let's say you're doing a group project, yeah? And let's say that teacher walks in and says, you 5 are a group. How many different groups could she have chosen? You don't care who she chose first, second, third, or fourth. You don't care the order of how they're sitting. So if you have one group of 5 kids, a permutation would say, oh, how many sit in this seat? 5, 4, 3, 2, 1. The same group of 5, there are 5 factorial different arrangements. That's permutation. But if a teacher just walks in and says, you're a group, for groups, that only counts as 1. That's a combination. So it's only one combination of kids, even though we could order them in 5 factorial or 120 different ways. Even though we could order them in 120 different ways, combination says, but it's just one group of kids. Does that make sense? So a combination says, there's one group of kids. I don't care what order they're in, just there's a group. But then if you take one kid out and put another kid in, that's a new group. It's a new combination. But we're not doing permutations because the order doesn't matter. It's kind of like yesterday when I mentioned about the committee, and that was actually the final example we didn't get to talk about a lot. The committee that we were choosing. This one. It was combinations as well, and here's the reason why. Because if you have these, what were we choosing? 3 kids, 1 admin, 3 faculty, and 2 students. If you choose 1 admin, 3 faculty, and 2 students, and they're in a room and they're on the committee, you don't really care who was chosen in what order or where they're sitting. You don't care about the order of them. Just, oh, these people are on the committee? Cool. They're one committee, even though they could be ordered lots of different ways. Does that make sense? But like the batting order yesterday, why did the order matter? It wasn't just the group of kids that were included. It was also what order, who was going to bat first, second, third, fourth, fifth. Those were different orders or arrangements, so we had to use permutations on that. So whenever you hear the word group or the word committee, you should think combination. Unless there's something that would make the order important, like, oh, but we're electing different people to different offices. And that's what I was mentioning at the very end of yesterday with, you guys loved the whole, not my president. But anyway, coming back. If there were offices that they were being elected to, different people could be elected to different offices, which would make a different committee with different offices. That would be a permutation. Okay, with that, we are going on to section 9.7, the final section of chapter 9. Let's see what we get through. Let's see how much detail we can get through. And I already took your attendance, so you're good to go on that. 9.7, before we start the notes, I just want you to read this. Maybe you'll write down a couple little key pointers, but for right now, just check it out. When solving problems involving counting principles, like and multiplication, repetition, no repetition, etc., you need to be able to distinguish among the various counting in order to determine what to use when. One of the hardest things in probability is figuring out what to use to solve the question that you've been given. Oh, P.S. I found this the other day. I was going to show it to you guys. In high school, it's very sad because the tape wore out. I was given an extra credit assignment for Pascal's triangle to write out And we couldn't really collaborate. It was just like whoever brings the most rows tomorrow gets extra credit. I had a little bit of fun. There's my Pascal's triangle. There's a lot. I went to row 50. Does anybody want to check and see if my numbers were right by row 50? How could we check like a random number in row 50? Calculator, but what? Yeah, NCR, right? So if I'm on the 50th row, actually it's the 51st row, but you guys know how the second row, right, I guess the third row had a 2, then a 3, then a 4, then a 5, and that could tell us what power. So I'm raising a plus b to the 50th power. Let's see, someone in their calculator, go to math prob, and let's do, r starts at 0, right? And then 1, then 2, then 3. What do you guys want me to choose? I technically have, what, 51 different options? What R do you guys want to plug in? 50, C, 14. Okay, so that'd be the 15th one, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I think I'm on the 15th. Because you said R, right? So I have to count over to the 15th term, because that's when R is 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Got it. 50C, 14. 50C, 14. What? $9.37? Ooh, my number might have gotten off. What's 50C2? C. $647. Anyway.
Did you get the extra credit?
Yeah, I got the extra credit because I had the most rows. But you see how sad it is, though? Because you know how sad it is? Because I was all nice and pretty and spaced, right? And then what did I realize when the numbers got way bigger? I had to expand. And so I expanded, started running out of room, and I was like, forget it, I'm done. But my numbers got really small. Mm-hmm. Yeah. I would pass it, except number 1 is falling apart, and number 2, my 50th row is wrong. That's kind of sad. Hey, do you want to check my 49th row? Real quick, do 49C3. Oh, so yeah, I went off somewhere early on. I'm off by like 40. Struggle. I think I was doing mental math, though. That might have been the problem. Okay. Pascal's triangle to the 50th row and show me how to do it right. Okay, no, let's not do that. Let's not waste time. Although it's fun. When facing a problem, I think what's more fun, though, would be fractals. Fractals would be more fun, like just drawing random shapes and then putting shapes within shapes and self-similarity, and that'd be more fun. Like what Beihart showed us with the doodling infinite, was it infinite caravan of camels or whatever? Well, the elephant one was cool. She did the elephant within it, and then elephants. But anyway. The 3 questions you guys need to ask yourself. Is the order important? If it's important, permutation. Are you choosing from a larger set where order is not important? Combination, which would be like our committee, like our group. Does the problem involve 2 or a combo pizza? Does the problem involve 2 or more separate events, like flipping a coin once and then twice, choosing one letter and then a second letter, hitting one stoplight and then another stoplight? You guys had no questions on 63? Huh. Okay. I didn't remember it was this homework, but I do remember that people usually hate that one. Oh, we do? Okay. Do we have any more questions on homework? Let's peek at 63. I totally expected it. Like I have it here ready to go, but I didn't think anyone raised their hands. All right, my ones. Come on, be honest. It's okay. My ones that didn't try it, you should be paying super close attention because you're super behind, at least kind of behind. 25 TV sets. A shipment of 23. The odds are that you're going to contain 3 defective units, which is kind of sad, but sets. Anyway, And how many ways can a vending company purchase 4 of these units and receive, ooh, all good units? How many ways can they receive all good units? Do I care the order? No. I just care whether they're good or not. I don't care what order I get the bad or the good when I open them up. So all good units. What's true if they have all good units? There are no defective ones, which means? Why wouldn't it be 25C4? The 3 defective ones are included in 25, so I can't do 25 because I'm not choosing from 25. If they're all good, I'm only choosing from 22. So out of the 22, I'm part good and part bad. Out of the 22 good ones, how many different groupings of 4 are there? Out of the 22 good ones, how many groupings of 4 are there? And you could also say, okay, and out of the 3 bad ones, we're not getting any. Out of the 3 bad ones, we're getting none, and out of the 22 good ones, we're getting 4. You can think about the and, because both of these have to be true at the same time. How many ways, how many groupings would have 2 good units?
5.
Only 5? I think there are a lot of ways that you can only get 2 good units, right? Because you have 25 different TVs coming in. They're getting 4 units. 2 of them are good, 2 of them are bad. Yeah, out of the 22 good ones you get, how many different ways could you get 2? But then you're also going to, out of the 3 bad ones, you're getting 2. Does that kind of make sense? You have to think about the situation. If you only have 2 good ones, well, then you have 2 bad ones. Oh, they're getting 4. 2 good, 2 bad. The last one gets a lot harder. Why is it a lot harder? So there are different possible ways that this could be true, right? What's one way you could get at least 2 good units? Yeah, having all 4 be good. So it could be like 22C4. That's one way. So all of those options, or, yeah, 3 be good, so 22C3, and 1 be bad, so out of the 3 you get 1. Or, out of the 22, you get 2 good, and then out of the 3 you get 2 bad. So you have 2 good, 3 good, 4 good. Now hold on. If this is a number of ways, and this is a number of ways, and this is a number of ways, and any of these are options, what operation am I going to do to put it all together? Adding, not multiplying. Because I have all these ways, or all these ways, or all these ways. All those options, adding all those options, adding all those options. So in sections 9.5, 9.6, 9.6, we talked about the fundamental counting principle. In one situation, you're getting 4 good and 0 bad, 2 good and 2 bad, 3 good and 1 bad. We always have to multiply with those operations, kind of thinking about if you needed to or wanted to count up how many outfits you had to choose from this morning. For some of you, it's not very many, but that's okay. Makes everything easier until you get to college and you're like, oh, I have to dress myself every day. Anyway, in different clothes, unless you're slightly judged, slightly, not as much as in like the working world. Coming back. Shh. How many outfits you had to choose from? Let's say you had 2 uniform, whatever, skirts, pants, shorts, whatever. 2. That's fairly normal. Maybe 3. Some of you might have 5. Good job. You don't have to do laundry as much. So you have, let's just to make it easy, you have 2 different uniform like bottoms. You have like, I don't know what, like 5 different polos. Is that somewhat reasonable? And you have, just to be silly because it's kind of cold outside, let's say 2 different heritage approved sweatshirts, okay? If you picked an outfit of a uniform bottom, a uniform top, and then a uniform sweatshirt, okay, or jacket, how many different options do you have to choose from? What would you think? Couldn't you, in a sense, put your, in your head, put your 2 different uniform bottoms, let's say like you had like a navy blue and then a khaki, okay? And with those uniform bottoms, you're like, okay, well, each of those I could put with the 5 different shirts, 5 different shirts. And each of those 5 different shirts, so now we have 2, and then that became 5 and 5 is 10. And then with those 10 different options of the uniform bottom with a shirt, can't we now say, well, each of those shirts could go with 2 different sweatshirts? So how many different options? This big old tree diagram where you have the 2, and then each of the 2, like a family tree, could go into 5, and then each of those 5 could go into 2 more. We have 10 total. Let's see. No, hold on. We have 10. We have 20 total different outfits. How can we do that with the fundamental counting principle? 2 times 5 times 2. 2 times 5 times 2. And you're like, oh, 20. But you could have also like actually drawn all that out. And that's why we have to multiply, is because every time we have a new option, that new option has a new category, a subset of what could be paired with it. So whenever we have one situation where we have an and, we're going to be multiplying. But whenever we're putting together different, totally different options, what are we going to be putting in between? Addition or. Addition or. Once again, why was it combination, not permutation? Yeah, order didn't matter. Here we go, probability. Probability says, hey, all that work was really, really good, but you're not done yet. Probability would say, let's take that situation in the page before. Probability would say, let's take that situation in the page before. And not just say, how many ways could you get all 4 TVs? Section 9.7 says, what are the odds, or what are the chances? What are the odds? What are the chances of getting all 4 good ones? Good TVs. And as soon as we have odds, we now need to make a fraction. And we need to say, okay, there are that many different ways of getting all 4, but how many total ways are there of just getting 4 TVs in general? That was of getting 4 good ones. How many groupings are there of 4 just total? What would we change? Someone throw it in the calculator real quick. Let's see what the chances are of getting all 4 good ones if out of a shipment of 25 there are only 3 defective. Or maybe in the midst of the shipping, you only have 3 defective. 22C4 divided by 25C4. Denominator will always be bigger because the biggest percentage you can have is 100%, even though coaches are like, give your 200%. Doesn't make sense. Yeah.
On one side of paper, do you want me to put another paper in the same back or start?
Probably just to finish chapter 9 be easier. Yeah. It's a good idea. 133 over, no, get me the decimal. 0.8 or 0.9? 82%. Okay. The odds aren't that bad. But how different were the combinations? Wasn't there just a slight little difference? There were just 3 more TVs that were included in that, right? And if we were to do something like chances or what are the odds of getting it, that would be your whole numerator, and what would be your denominator for the whole thing? Same thing. C4. What are the total? And what are the number of groupings that fit that specific characteristic? Okay, so with that, getting the difference between 9-6, how many ways, how many ways, how many ways? 9-7, what are the odds, what are the chances? We're going to have to put together 2 different how many ways total and how many ways for a special condition to get the odds or the chances, which will be making decimals into percentages. Okay, I'm back. Vocab you might see. Outcomes, sample space. Ooh, I already talked about that one. And then in general, probability is the number of ways a specific event can occur divided by the number of ways possible in the sample space. Outcome is a pretty standard English word, right? Outcome. What would you guys describe outcome to be? It doesn't really have a special math meaning per se. Result. Is it an actual result or is it a possible result when dealing with probability? It's usually a possible result. It's not usually you're actually testing it and then checking, oh, hey, I happened to do this. I wonder what were the chances before. Like usually it's a prediction in a sense. Usually it's a foreseeing and trying to think through. I mean, you guys are more familiar with odds and chances than you are with a lot of different math topics. So outcome, usually it's a possible outcome. Usually it's a possible result. There's a key word up here, favorable. It's actually meeting a certain condition. Like what are the chances if you flip a coin once you get heads? 50%. If you flip a coin twice of getting heads? 25%. Flipping a coin 3 times of getting heads? 12.5%. Anyway. But then you could say, what are the chances of not getting a heads? And you'd be like, well, it could be getting a tails. I mean, or it could be, ooh, flipping on end. That rarely ever happens. So, unless you have a 2-headed coin, which is awkward. But, and cheating. Anyway, possible results are the outcome. Sample space is the combination of the favorable. Am I spelling that right? That was an O. Favorable. You could think of the combined number, not like that, but the combined number of favorable and non-favorable outcomes. So it's everything. Like, what are all the different possible results? All of them. Doesn't matter, favorable, non-favorable, put them all together. What are all the different possible results? That's the sample space. The outcome, if you're talking about favorable, you're talking about for a certain condition that must be met. Non-favorable, the opposite of that certain condition being met. But in general, as we talked about, section 9.7, small numbers, fractions, etc., because we have to take, when we're finding the probability of an event occurring, think about favorable outcomes for a certain event or a certain condition. We're going to have the number of ways, which is good wording from section 9.6, but for section 9.7, we'll say the number of favorable outcomes for whatever condition they're giving us. The number of favorable outcomes for the event. And on bottom, it'll be the number of, or in the sample space. The total number of outcomes, favorable and non-favorable combined, which is what you guys saw us do with of getting 4 good TVs. It was like, okay, well, how many ways, how many groupings of 4 good TVs are there possible? Okay, but how many groupings are there total good TVs and bad TVs all included? Colby. I mean, it's a science, right? Like meteorology, it would be an actual study, so it's not just chances. But are probabilities greatly involved? Yes. But there are also a lot of like wind patterns and weather patterns and vectors and all sorts of other stuff that's being applied also. Programs, weather balloons, huh? Well, horse races, gambling in general, there is an art to the very imprecise science. Some of it is experience. But when they're running the odds and whatnot, they probably have set systems that they're following as far as when you win, when you lose, what the odds were against you or for you, etc. I honestly haven't been to horse races, so I can't really say much besides what I've seen on different shows, etc., as to how it's done. So I don't know entirely the entire system. And I know that there are different systems based on different individuals as to how they're placing the bets, but how they pay out, I'm sure there's a set system that they follow. And a lot of it is based on, even with like betting on games and stuff, talk to Jared Epram, he could explain to you much better than I could, but there's the idea of if the odds are against you and you win, you usually have a much bigger payout, right, than if the odds are for you. Of course, and there's the may the odds be ever in your favor, but we won't go there. Hey kiddos, P, what do you think P stands for? If N stands for the number of ways, N for number, what do you think P stands for? Probability. And this little notation, the parentheses, I'm not multiplying. It's function notation. It's probability of, right? Like f of x, the number of ways of the event, the number of ways of the sample space, etc. So when you see this P of E is 0, that's saying the probability of an event occurring is 0. Ooh, so if the probability is 0, what's going on? S is sample space, E is event, N is number of ways, P is probability. E is an impossible event if the probability is 0. Then it's a completely impossible event, aka the event will not be occurring. What's the probability that it's raining right now? 0, because there is no rain right now. Now, can I say what the probability would be in 5 minutes? No. Or tomorrow? No. Or Thursday? Definitely no. In Santa Clarita, I think it's 20% tomorrow. Thursday, it's 60% chance. Anyway. But I can say right now, the probability of it raining is 0, because right now, this very split second in time, it's not raining. There are not many things that we can say the probability is 0 to, right? Our times are uncertain. What's going on in the second one if probability of E is 1?
Will occur.
Will occur? Yeah. Isn't 1 kind of low, though? It's 100%. 1.00. So if the probability is 1, then the event will occur. And we would say that this is, for one way of saying it, a certain event. E is a certain event. It will certainly occur. It is assured. Those of us that believe in the Bible, we would say God getting the victory at the end of all time is a certain event. What's the probability that we're doing math right now? 1. 1.00, 100%. Okay, letter A. So quick heads up. Probabilities, that's the range, 0 to 1. Seems kind of small, right? But if you think of it in terms of 0 to 100%, well, now we have a lot more options. But 0 to 1, just think these numbers are small. You toss 2 coins. What is the probability that both land? Ah, we already answered this. But how did I answer 25%? Did I think of all the possible options of heads, heads, tails, 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 heads, and heads, tails? Did I think of that and say, how many times will I get both heads, 1 and 4? Maybe. Maybe I thought of 1 and 4. Did I think about fundamental counting principle and how I'm throwing a coin 2 different times and I have 2 options in both? Wait a minute. How many different ways can you flip 2 coins? How many different orders can you get? 4. But hold on. How many favorable orders? Just 1. Heads, heads is only 1 possible out of the 4 would have gone on the bottom. The 4 would have gone on the bottom because you have 2 options for the first, 2 options for the second. But on top, you only have 1 option, heads, and 1 option, heads. So favorable outcomes, well, it's just 1 and 1, heads and heads. But on the bottom, it could have been heads or tails, heads or tails. Another way of getting 1/4. What are the chances of getting heads on 1 flip of a coin? And getting heads again? What's 50% times 50%? Or what's 1/2 of 50%? However you do it, there is 1, 2, 3 different ways, and that's just for this one problem. Some use the fundamental counting principle, and some way, well, these 2 use the fundamental counting principle. These 2 say, well, you better be able to visualize all the options and count up the good ones. That gets hard once you get into a bigger situation. Andrew?
Do we write this 25% or do we write it as 0.25?
Never write it as 0.25. The book sometimes is going to give the answers in fraction form, like 1 and 4. What are the odds, 1 and 4, or 1/4? What The chances are almost always 25%. What is the probability? Almost always a percentage. As long as you know that they're the same, I'm okay. How about letter B then? The other day we realized you guys need to play more card games. All right, let's see what we can do. The tutorial card has hopefully been pulled out, otherwise it's super annoying. The Joker's standard deck, we'll say the Jokers are not being included. It would be in the box, but a standard deck, if you're using a standard deck, you're not playing with Jokers. So therefore, how many cards are there total? Some of you need to write this down to refer back to it. In a deck of cards, a standard deck of cards, total. Tell me some other stuff about a deck of cards. 24. 26 red, right? 26 black. What else? Something else important to do with numbers. There are 4 suits of 13 cards, right? And then there are 4 face cards in each suit. So if there are 4 face cards, how many numbered cards are there? Jack, queen, king, depending on how you're counting ace. We count aces as face cards. I mean, sometimes aces are low. So then 9 number cards. If you want to split it up, you could go ahead and say how Colby did. 3 face cards and then 1 ace, if that's helpful. Okay. Whew. Those are all that is pretty much all the info that you would need. Unless there are Jokers, then you would have to up the number of cards and then up the red and black. But no, Jokers don't have a color assigned, do they? Oh, they do. All right. But you wouldn't up the suits because there isn't like a Joker per suit. Coming back, they're saying you draw 1 card at random. What's the probability? It is an ace. 4 out of, which is the correct answer, but you could also reduce it because there's a group of 4 into 52. That's 13, right? The number of cards per suit. So you could say 1 in 13. But technically, wouldn't both of these be the same percentage, the same odds? It just looks a little different, but 1 in 13 would be the reduced odds. What if we have and? Keyword and. Hey, it's a Venn diagram. Go team. And. The probability of events A and B occurring. Now, some of you are like, well, we did and last section. It's no big deal. We just multiply. But this might be a little different. This might be what is the probability of getting a black. Should I go crazy right now? Yeah, we'll do that. Probably. Why is this an and if it's a black ace? Like it's one situation, you're picking 1 card. What's the probability of getting it to be black and an ace? You can think of all the black cards, right? And how many black cards are there? 26 total. Think of all the aces. 4 total, but wait. If you take all the black and all the aces, you're not going to have 30 cards. You're going to have just 28 cards because how many non-ace black cards are there? 24. How many non-black aces are there? And how many black aces are there? Does that make sense? So then here's the 26 black cards, here's the 4 aces, and there are the 2 that have both. For the Venn diagram, if you're able to hold in your head the whole situation, you can be, oh, 2 of the aces are black. There we go. So the probability of choosing 1 card, choosing 1 black ace would be 2 out of 52, right? Or 1 out of 26, if you were just picking 1 card. So a Venn diagram might help, but if it's something where you can't necessarily hold all the options in your head and think about how many are shared, there is a way of thinking about the probability of A and B occurring. And it's not 2 separate events, it's like 2 separate characteristics in a sense. and we would use for the word and, we could make, we'll kind of go back to geometry and use the intersection symbol, which would be an upside down U, which looks kind of like an A if you were just to draw the line across. A for and, the upside down U. And we do the probability of A occurring times the probability of B such that A has occurred. Let me go ahead and translate that just a little bit for you. B such that A has occurred. Yeah, notation for and be the upside down U. So what if we were to have, you guys ready? So be careful with the word and. There are two different ways you can see and. One is there's more than one characteristic being true at one time, which is kind of like a Venn diagram idea. Is there any overlap, etc.? But sometimes the and is just like it always was, or like it was the last section, where we just have three separate blanks. This one, is it all one event occurring, or are there three separate events that are occurring? You can kind of look at it two different ways. You can look at the computer choosing all three numbers, one event, or you can think of it choosing a first number, second number, third number, three events, right? So we see the integers that it's using 1 through 20. Let's try to think through what's the best way of thinking or answering this question. What is the probability? What are the chances? What are the odds that all three numbers it chooses are less than or equal to 5? All three numbers are less than or equal to 5. Well, how many numbers are there less than or equal to 5, first of all? How many ways can this occur? Yeah, because 1, 2, 3, 4, 5, 0 is not included. So there are 5 different ways this can occur, right? So what would be the chances or the odds of choosing one number less than or equal to 5? 5 over 20 or 1 over 4, right? But it has to do this how many times? So you could think of it two different ways. Either you can think of it as, well, it has 20 to choose from, 20 to choose from, 20 to choose from. That's the sample space. But on top, it has 5 to choose from, 5 to choose from, 5 to choose from. That would be the number of ways the event could occur. You could think of there's a 1 in 4, 25% chance times 25% chance times 25% chance. That works too. It's the same exact math. Or you could also think of, if it would be helpful, out of 20 total, choosing permutation, repetition is not allowed. Out of 20 total, choosing 3, and out of 5 total, choosing 3. I think that would be the same, 5 factorial over 2 factorial. We'd have to check that tomorrow and see if there's a way to actually use combinations or permutations as well. Some of you guys already figured it out, though. What was it? Yeah. One point? That's over 100%. Oh, 0 point. 1?
0. 0, 0, 1.
Bye, guys. Get into it as far as you can until you get stuck, and let me know tomorrow where you got stuck. I'm listening to too much noise right now. Oh, 565. Got it. Bye. There we go.
Can I do the homework like after school or something? Like, is there any way